right. So we are here. We are going to finish up chapter 4 finally. How long have we been in chapter 4 now? Like two and a half weeks or something? Boy, that sure is a long time, huh? But it's okay because all the material in chapter 4 was super easy and super straightforward. And it wasn't confusing at all. And what other misinformation can I spread? All right, well, I think you guys get the point, right? There's a lot of information in chapter 4. We cover a lot of reactions. We cover stoichiometry, which is a huge important topic. Right? We cover limiting reagents, which is a big important topic. We cover oxidation states, which is extremely important as we go through organic chemistry and as you guys go through, even in biochemistry, even though the biochemists won't admit it. It's because they're doing it wrong. Right, but anyway, right, you guys will figure that out when we get there. But, so we got a lot of important stuff in chapter 4, okay? We will have a quiz on Friday, okay? Let's see, our last quiz was on the end of chapter 3. So we'll start going through the beginning parts of chapter 4 on the next quiz. If you guys haven't picked up on the patterns of things yet, I will never give you a quiz on stuff that we've just done, right? So what did we do at the beginning of chapter 4 is basically what the quiz is going to be on, right? The different types of reactions and balancing reactions and all this other kind of stuff that we kind of came out of. Right? So we probably will have some oxidation states and stuff on there. We probably even will have some limiting reagent or that kind of stuff on there too. Okay? So make sure that you guys are spending the appropriate time practicing these problems. I think I've already given you guys my spiel about why I want you guys to be prepping for all these quizzes all the time, right? So remember the exam is coming up in 2 weeks. Is that basically what it is, right? About 2 weeks, right? And so we've got even one more chapter to go on there, right? Another challenging chapter. So we definitely need to make sure that we're practicing appropriately along the way, okay? So we'll get started with some prayer, and then we'll finish up chapter 4, and we'll launch into chapter 5 then. But Lord, we just thank you yet again for another day, Lord. We just thank you for another opportunity. And we just thank you for the blessings that you provided our way this day, Lord. Just being able to get up and just, breathe the air of a new day, Lord. It's just a blessing that's undeserved for all of us, Lord. We just thank you, Lord, that you love us. We thank you that you care for us. And we just pray today, Lord, just to understand your love a little bit more. Or just help, just unravel yourself to us in whatever way, Lord. We pray that you just speak to our hearts. Lord, we know that each of us are on a path. We're all on a different stage of that path, Lord, and we just pray for your guidance along there. We just ask all this in your name. Amen. All right. So, we had one last problem here, which is kind of the culmination of everything. It's the idea of molarity with limiting reagents, and then trying to find products and doing the conversions and all this kind of stuff kind of getting mixed together. Right? So I believe we started out by doing the first thing, which was writing our balanced chemical equation. And then the question is asking for which reactant is limiting. So to do a limiting reactant problem, what do we need to figure out? Well, we need to figure out which of our starting materials, which of our reactants makes the least amount of product, right? That's what the definition of our limiting reagent is. It's going to make the least amount of our product. So what we got to do is we got to figure out how much product is going to get made from the iron 3 chloride, right? And we got to figure out how much product is going to get made from the sodium hydroxide, okay? That's what we got to do. This is where these, when we first introduced this idea of limiting reactant, right? This is where we did our gram to mole, mole to mole, mole back into gram conversions, okay? We compare our reactants to our products and figure out which one makes the least amount of product, okay? What's different about this problem? Do I give you information about grams? No. Do I give you information about moles? Sort of, right? I give you information about what? Volume and molarity. And if you multiply volume times molarity, what do you get? Moles. So what should be the first step that you guys do here? Volume times molarity, right? Just paying attention to what? We have units of milliliters, so we need to convert that into liters, right? per liter. That tells us I have 0.0585 moles of FeCl3. Okay. Taking my concentration times my volume, gets how many moles I have to begin with, right? So same thing with my sodium hydroxide. Do that in red, so 0.453. Uh, 0.0225. Good. So what does this tell us? Oh, well, we have less moles of the iron 3 chloride, so that's limiting, right? Is that how it works? No. Is that how you get things wrong in exams?
Yes.
Yes, right? I don't care necessarily how many moles of the iron 3 chloride I have. I care how many moles of iron 3 chloride produce or react to make my product. So what do I have to do? Convert moles into moles, right? Moles of FeCl3 into moles of the iron hydroxide, or moles of the sodium chloride, it doesn't matter, okay? So set up that conversion. So 0.00585. See, for every 1 mole of FeCl3, 1 mole iron hydroxide, iron 3 hydroxide, I should say. We got very tricky math already this morning, okay? So 0.00585 moles of iron 3 hydroxide. Perfect. 0.065 moles of sodium hydroxide. For every 3 moles of sodium hydroxide, 1 mole of iron 3 hydroxide, 0.0075.
The iron chloride stuff still leads to a smaller number then, so that is limiting.
So where am I getting these magic numbers of 1 and 1 and 1 and 3 from? That's from my our stoichiometry, right? My balanced chemical equation, right? If we have the wrong balanced equation, then it throws off our math. So again, then we have to stop and ask the important question of, we did a thing, now we should analyze thing, right? What do these numbers tell me? Right? This is an important part. What do those numbers circled in black tell me? They say, if I react all of my iron 3 chloride, I make that much product, okay? If I react all my sodium hydroxide, I make that much product, okay? That's what those are telling us. We are assuming, right, in that math, that starting material gets completely consumed, okay? That gets completely consumed to make the maximum amount of product. Whichever makes the least is our limiting reagent, okay? That's just the way it works. Okay? So it just so happens that we still have our iron 3 chloride as our limiting reagent because it makes the least amount of product. Okay? You guys with me on this one? Okay. So if the iron 3 chloride is my limiting reagent, what about the sodium hydroxide? It then is my what?
Excess.
My excess reagent, right? So sometimes the question asks, what's the excess reagent? Or how much of my excess reagent is there, right? These types of questions that come up. Typically, we only see one thing as a limiting reagent, okay? Sometimes the book gets super duper tricky and puts two things as a limiting reagent. Good? Cool. I think we finished that up then, right? This question asked for which reactant is limiting, right? That's this guy. And then how many moles of iron 3 hydroxide will form. So we did kind of both things in one single step there, right? Neat. Yeah. Yep.
How do you get the amount of excess left over?
Yeah, good question. Thanks.
Would that just be subtracting the amount of the limiting reagent from the amount of the excess?
Not quite, right? So the question was, how do we figure out our excess reagent, or how much of our excess reagent is left over, right? So I'm just erase some stuff here. So if this is our limiting reagent, okay, what we need to do is compare our limiting reagent to our excess reagent. So again, we just have to convert moles to moles, okay? So here's what we do in this case. See, if I start out with 0.00585 moles of FeCl3, I need to convert that into moles of sodium hydroxide. So for every 1 mole of FeCl3, I need 3 moles of sodium hydroxide. So someone needs to help me with the math here. So what is it, 0.016 something? So somebody can do that for me real quick.
0.017.
0.017? 0.017. Anyway, 0.055. Cool. So again, we stop and we ask the question, what does this number tell me, right? This number tells me, right, that if I need to consume that much, right, that much of my iron 3 chloride, I need to use that much sodium hydroxide. You guys with me on this? Do I have at least that much sodium hydroxide? Yes, I do. I've got what? 0.02265. You guys following along with this? If I use all of this, I use that much sodium hydroxide. That's what this number tells me. Good? So how do I figure out how much I have left over?
You subtract that from the original.
Right. I
excess.
start out with 0.02265 minus that right there. So it comes out to what, 0.005 something, like 5 and some change. Good? I can tell. I'm looking at everyone's eyes, I can see the complete understanding just oozing. What's up?
So we've got 0.017 moles of sodium hydroxide. That tells you how much you would need.
This is how much gets used to react with all of that. That's what that's like. Because I need 3 of these for every one of those.
So you need that much to react with all of it?
Yes. So this gets completely consumed. Then the question is, do I have at least that many moles of sodium hydroxide? Up at the top there, yes I do, right? And then you just subtract those 2 values and you get your excess left over. Okay. How's the math different for this here? The answer is, it isn't, right? All we're doing is a mole to mole conversion. The difference comes from when you ask yourself at the end, what in the world does it mean, right? What in the world do these numbers mean? There you have to talk yourself through it. What does this tell you, right? What does this tell you? Okay. Cool. So let us then change gears here. We'll go on to the next chapter that caused everyone much pain and misery. Yeah. Uh-oh. I thought I opened it already. Alright, so give me just a second here. I've got to convert, I thought I'd convert this over, so. Take a quick 5 here, I got a slight technical issue. Okay, alright.
I love all this.
So, we get into chapter 5. Now, chapter 5, we're gonna learn really one equation, alright? It's really gonna be down to like one equation that answers about 90% of the problems that come out of this chapter. But there's some tricky stuff along the way too, and we have to talk about some other, let's say, math along the way and these kind of things. But I guess at the end of the day, what becomes challenging from this chapter is just the way that the questions are asked. Like the way that the book asks questions out of this chapter is particularly challenging. Okay? So we really have to pay attention to how and what and who and where and all this kind of stuff. Okay? So one equation. So if you ever get stuck on something, just kind of go back to that one equation there and see if we can figure out the information and plug everything into it. Okay? Or we're going to be talking about the idea of thermochemistry, right? Or it might even be called thermodynamics. Right? All we're dealing with is a transfer of heat. Okay? Whether heat goes into or out of a reaction is really kind of where it comes down to. Okay? Now you guys already kind of know this idea. You guys ever used one of those ice packs that you have to like break the little capsule that's inside of it and it turns cold, right? So that's just thermochemistry, right? You have a salt that's dissolved inside of those things. I think it's ammonium chloride is what it is, right? And when you dissolve that into water, it just absorbs heat from the outside and turns cold, okay? And so then you can use that, you put on your Herschel or whatever it might be, same idea, okay? So we're just gonna be able to calculate how cold something can get, or how much energy gets transferred from the universe into your ice pack there. That's all it comes down to. So we're just gonna be dealing with energy is what it is. So the first part of this, we're gonna talk a little bit about what energy is. Okay, we're gonna get a little bit of definitions here and there, right? And then we're gonna talk about heat flow into or out of something. Now, I'm going to give you guys a lot of slides here at the beginning, and we're just I'm just going to scroll through them, okay? I don't need to sit here and read you guys a wall of text. You guys have all my notes online, right there. I'll have access to them there, right? They just come from the book anyway, right? In terms of summaries of the book, right? So I want you guys to read through that stuff, but I don't need to sit here and bore you guys to tears with this stuff either, right? I'd much rather spend time working practice problems with you guys in here, especially from this chapter. So we're going to go through a couple of things here at the beginning, right? And then I expect you guys to kind of follow through some of this stuff that we kind of gloss over, okay? All right, so let's get it going. So we talk a little bit about, or at the beginning, the book kind of just talks about physics is basically what it is, right? And so if you're like me, physics is all math, and I've told you guys that math and me are, we have our bad days, right? But anyway, we talk about energy, and that's the capacity to do work, and then the question becomes, well, what in the world is work? And that's, we get a definition of it, and blah, 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 work equals force times distance, and all these kind of things. Fine, fair enough. I think you guys have to go through physics at some point. If not, you guys have probably learned this in high school or heard it or something. Who cares, right? That's not too much chemistry that we need to deal with that stuff there, okay? What is important, what we will talk about, is what in the world energy actually means to us in the perspective of chemistry. And there's really only two types of energy, which you guys already know. What are they? Kinetic and potential, right? So kinetic and potential is really all we care about. Now the question becomes, how do those relate to us in the context of chemistry? Okay? Because energy is energy, right? So now we already talked a little about kinetic energy in this class, right? Way back when life was easier, in chapter 1, we talked about what? Some theory. Yeah, you guys remember that? Kinetic molecular theory? What does kinetic molecular theory deal with? Well, it deals with a theory about the kinetics of molecules, Dr. A. Yes, it does. You're right. So what do we mean by kinetic energy? The energy of motion, right? Is kind of what the broad definition is, right? So now we're talking about, kinetic molecular theory, the motion of molecules, right? Just whether molecules are moving around or not. And you remember we related that to solids and liquids and gases, and how much the molecules are moving, and all these different types of things with it, right? And so when we're dealing with kinetic energy, and here's where we're getting into the relation to this chapter. How do I make things go faster? Yeah, give it some energy, right? If I wanted you guys to start answering more questions, what would I do? Bring you guys all donuts covered with sugar, right? Give you guys a whole lot of energy, and you guys would be bouncing around. Yes? No? What do you guys want then? We want the, you okay?
Yeah. I dropped
Oh.
my pencil
Oh.
and the magnet.
I thought you were like trying to sneak up on me and take out my hamstring or something. All right. Right? So if I give you guys a lot of energy in the form of sugar, you guys would be bouncing around, right? Well, I don't know. It's still 8 o'clock, so maybe not, right?
And some caffeine in there, and man, you can
There we go.
throw me off the ceiling.
There we go, right? So when we talk about kinetic energy, we're just talking about giving something energy. Now, how do we give something energy in the chemistry world? What's the easiest thing to do? Yeah, heat something up, right? And it's the reason why you have to boil your spaghetti water before you put the spaghetti in there, right? Otherwise, what? It's going to take a long time to cook through all the different starches and stuff that's in the pasta, right? So we have to give it some energy to get the reaction going and start to loosen things up and that kind of thing, right? So that's why we're dealing with the transfer of energy, thermodynamics or thermochemistry, right? Energy going into something or energy going out of something. Potential energy, we'll talk a little bit more towards the end of this chapter, and then we'll talk about it more, I believe, in chapters 6 and 7. Or is it 6, 7, 8? We're going to talk, there's 2 chapters that we deal with making and drawing the structures of molecules. And so potential energy for us is in the bonds that get formed between atoms, okay? And so we're going to have to learn a little bit about information about how we know when certain things are bonded together, right? But you guys already knew that there's potential energy stored in bonds, right? Because otherwise our combustion engines wouldn't work, right? You have to burn gasoline and we get energy out of that, right? So we have to break bonds and make bonds, and energy gets transferred as we go through that. All right, here's stuff. Good. Okay. Here's more stuff. Good. Okay. Here's some interesting definitions. We'll stop for just a quick second. Calories, big C, small c, all these kind of things. The only real thing to point out here is that we will be dealing with, typically with units of joules, is what we measure energy with, especially for this chapter, right? And just kind of the relation of what lowercase c is to uppercase c in terms of calories and what it is to joules and all this kind of stuff. You guys will see this number come up again later in a different context, right? So we'll see this 4.184 come up. It'll actually probably be a number that you guys will just end up memorizing, but I give it to you guys also on the whenever you guys start going through your exams, okay? So just a little bit of definition there is all it is, okay? Cool. All right, we know about conservation of energy, right? This is what we talked about way back in the beginning also. Energy can either be created or destroyed. Cool, got it. So what does this mean for us? So what this means for us is that everything has to be equal to 0, okay? That's what this tells us here, right? So if I put energy into something, that energy has to come out of something else. That's what it tells us, right? That's all it's gonna end up meaning for us. So what we're gonna do in this chapter is we're gonna balance the universe, okay? So much like the Jedis, right? We have to maintain balance with everything here, right? So what I put in has to be what I get out. And that's gonna help us simplify the math, but we have to remember that. Everything has to add up to be equal to 0, okay? Because we can't create or destroy energy, okay? Alright, so you guys got this. This is very much physics, right? You put energy in, it converts to kinetic, yada, 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 yada. We got it, alright. Energy and work, okay, good, check. Temperature, thermal energy, alright, yeah, okay. So this is what we were talking about with kinetic molecular theory, right? When we put energy into something, we start the molecules moving, the atoms vibrate, the atoms balance, the atoms rotate, right? The molecules do the same thing, they vibrate, they rotate, they stretch, they bend, right? We'll learn a little bit more about that when you guys get to organic chemistry, exactly how we can measure these kind of things, right? But the higher the temperature, the faster the motion, and we got that, okay? Cool.
Quick question.
Yeah.
What about for those of us who have not ever dealt with physics?
Cool,
and
yeah.
They're bad at it.
Okay, well, that's a fair question. You know, what should we do if we haven't quite been through a physics course yet? What I would say is, you know, go through and read through those slides there then, right? That's about the basics that you need to understand for it, right? And if those don't quite make sense, then come see me and you can talk through a little bit more with that, okay? Yeah, what's up?
Oh, that says atoms of all materials are always in motion.
Correct, yeah.
So,
The
solid,
table is vibrating.
yes, at a certain point, but is that why everything melts?
Is that why everything what?
Melts.
Ah, so interesting question, right? So, let me back out your question here for just a second. So as you add energy into a system, right, no matter what it might be, right, water or ice or whatever, right, the molecule starts to vibrate more, right? Now, we theorize or we think maybe because we deal with water so much in the day-to-day life, that everything will have a melting point where it turns from a solid into a liquid, right? But your desk isn't gonna melt, right? What'll happen is eventually it'll just start to decompose, where it reacts and turns directly into, turns into CO2 and water, or it starts to burn is what it is. So in principle, you're correct, right? If we just take maybe a theoretical universe where this doesn't exist, right? Everything would go from a solid to a liquid to a gas, right? But in practical terms, right, not everything does have a melting point. We could just heat things up and eventually it's gonna decompose. Because you're gonna add enough energy into that system to start to break the bonds apart, right? That's what decomposition is. You physically break apart bonds between carbons and oxygens and that kind of thing. Melting is just where you have enough energy where the molecules start to slide over each other, okay? So we turn things from a solid into a liquid, right? We have the free flow of the molecules, right? That's why when you grab a pitcher of water and you pour it, right, there's a flow of water is what it is. Right? These molecules are tumbling over each other, right? So that's an important distinction, but it is a good question, right? And then your follow-up question is, well, how do we know when that happens? And I will say, good question, we'll answer in about 2 chapters, okay? Okay? Yeah.
So is the relationship between water and ice, where, the point at which water becomes a liquid,
Yep.
essentially in like effect kind of the same as the point at which, a metal like the iron is heated to the point that it basically becomes a molten liquid?
What do you mean by that?
Well, so when water is frozen,
Mhm.
it freezes into a very specific molecular structure of the ice. It's actually less dense than the
Liquid water, yeah.
which is obviously kind of liquid water. Obviously, in this case, the density isn't really going to decrease with the solid, but is the way that the bonds kind of like freeze into a position and like sort of hold their distance between each other gonna be sort of the same as between ice and liquid? Or
So if I'm understanding your question properly, is there any correlation between the arrangement of molecules in the solid state as in the liquid state? Depends. But this is actually, it's funny you asked that, and there are I would venture to say hundreds of scientific articles written even through today that ask or debate that idea, right? How much correlation is there between the solid state and the liquid state? For certain molecules, the answer is not much at all. For some, the answer is they're very similar. But the question then becomes, is it local, right? Is there a localized order, or is there a long-range order of these molecules, right? That's what the difference is. It's kind of like with, you guys have heard about glass being an amorphous solid, right? That means it has localized order, but not long range, right? So localized, it might look exactly like if it was in its solid state, but long term it won't, right? So that's kind of the idea there. So the answer is, it depends. much like most of chemistry, right? There's a lot.
These questions have it depends.
I know. There's not many black and white answers in chemistry is what it comes down to, right? So, no, that's what makes it interesting to study, right? All right, so, well, I don't know, it makes it interesting to study for me at least. But for you guys, it just frustrates you, which I apologize, right? Well, not really, I don't apologize. I can't apologize for science. Right? But anyway, so here's the first thing that I really need you guys to pay attention to, right? So snap back here with me for just a second, right? So one type of question that we're going to ask in this chapter, which is going to show up on the exam. There's going to be a question on the exam with this stuff, and it always shows up on everything, just because it's an important question to ask. But so anyway, how do we start to look at the transfer of energy? Okay. Now, the second bullet point on here is important. Okay, because it talks about if, right? If we heat always flows from something hotter to something colder. Now, you guys already know this. Because really, remember, what is heat a measure of? Heat is a measure of energy, right? So what my statement there in bullet point 2 is things always flow from something to nothing. They always flow from high to low, right? Because I could have just asked you guys a question. How does wind form? You guys all know what wind is, right? But how do we get breezes? What physically happens when a breeze gets formed?
A hotter body of air pushes around a little body of air, and instead of mixing, they kind of like push against each other and that creates.
Sort of, right? It has to deal with pressure, right? High pressure, right, to low pressure is how wind starts to flow, right? Now the question is, how do we get pressures, and then we have to deal with temperatures and densities and all this kind of stuff that comes with it, right? But all these ideas are kind of work off the same principle. A lot of you guys have been going through biology, right? Have you guys talked about osmosis yet in there, right? So how does osmosis work? It goes from high concentration to low concentration, right? That's the extent of my biology knowledge. So if you guys are wrong, if I'm wrong, please tell me, right? But that's how it works, right? You guys done that like starch lab yet in biology where you have to do the iodine and it turns blue and all this stuff? No? Yes? Okay, sorry, I'm spoiling the future for you guys then. Hint, it turns blue. Okay, all right. All right, you guys will figure it out when you get there, okay? But that's just the nature of everything in the universe is really what we come down to. We flow from high to low. Now, what does that mean for us? We have to know the energy of both of the components, right, that we're mixing together. The thing that has higher energy, right, listen, this is going to be important. The thing that has higher energy is going to lose. The thing that has lower energy is going to gain. Now, I can tell, because no one fell out of their seats, that you guys aren't shocked by that statement, okay?
My world has been so shattered.
I know. But you guys get the importance of this. If we mix two things together, something has to lose and something has to gain. What do we know about the values? The thing that loses, right, that same amount of energy has to be gained. Why? Because the universe has to be equal to 0, right? So if I lose 100 joules of energy, what happens? Something else has to gain 100 joules of energy. You guys with me on this? That's going to be the math. Wow. Now, I think you guys followed along with me on this, okay? But then we're suddenly going to start asking confusing questions, and it's, oh no, what is he? It's the same thing. Something has to lose, something has to gain. Whichever one loses has a higher energy to begin with, whichever one gains has a lower energy to begin with. That's what we have to start to pay attention to. Okay? Yeah, you have a question?
And something like this, like the experiment that's pictured with lowering a hot metal bar into the water,
What, are you saying I gave you guys a bad example here? Jeez. This is just, I think this picture is still in the textbook. If not, it was in one of the older versions. They're just kind of visualizing what's going on, right? We heat a piece of metal super hot, we stick it into water, the water increases in temperature. Now, where that energy actually goes is a different question, right?
A lot of that heat is gonna rise as steam, and as it evaporates, it's actually gonna lower the temperature of the water, so a lot of that energy is gonna just like kind of not really be quantified.
Right, so your statement is, Dr. H, things are complex. And I will 100% agree with that, right? And so that's why when I ask you guys these types of questions, you have to make a couple of concessions. And I'll usually say something along the lines of, in an ideal system or in a closed system, these kind of things, okay? And I believe you guys will be doing an experiment very similar to this when you guys are in the lab. You're gonna be taking high-tech styrofoam cups, okay? Now, they're science styrofoam cups, which means what?
Dr. Thomas stole them from the cafeteria.
Yeah, probably. Right? But so you guys will be doing an experiment similar to this and measuring some of the temperature changes as you dissolve things and transfer things, right? And so there are, as Rachel was pointing out, energy gets lost into the air or it gets lost into the cup itself and these kind of things. So there are certain concessions that have to be made, and we kind of work in an ideal world is what it is, right? And so if we, I know we don't have an engineering school here, but if you guys have any interest in engineering, or if you go on to that, you guys will spend the rest of your careers dealing with the heat of or the flow of energy, and so you guys will understand a little bit more about where everything goes, right? But the point that I want to get back to is these are thermal equilibrium questions, is what these are called. When I put something hot and something cold together, at the end of the day, we assume that both of the temperatures are going to end up being the same for whatever was hot and whatever was cold. They're going to reach an equilibrium with each other, okay? So the final temperature for everything in here is going to be the same. And that's one of the assumptions that we have to make, okay? So if we let this experiment play out and we just left that iron bar or whatever metal it is, if we left that in the water, at the end of the day, everything would end up having the same temperature, the water and the iron bar itself. And then we could measure that change in energy, and we could back out certain important information from that is what it is, okay? So take a look for these, anytime you see that keyword equilibrium in terms of, with respect to this chapter, right, they're gonna be setting up a certain type of problem for you guys that we solve in a certain way, okay? And don't worry, we'll walk through a couple examples of that. All right. How much time do I got? Oh, plenty of time, good. All right, so a little bit of definitions here. We got the system, we got the surroundings, and we got the universe, okay? So the system is basically what we're looking at, the beaker, the container, the box, whatever you guys want to imagine it is, okay? So the surroundings is everything else, okay? And then the universe encompasses the system and the surroundings. And so this is our first foray into the expression here, right? If the system gains energy, the surroundings have to lose energy, but the universe remains zero, right? That's all this math is setting up for you guys. So we really only have a 3-component system, okay? I have to give you information about 2 of those. I have to give you information about the universe, or the system, or the surroundings, and then you guys can figure out the other one, right? That's all it really comes down to. But you guys already have information about the universe. What happens to the universe? Nothing, right? It's always going to be 0. You guys with me on this? This is important. The universe is always 0. So what does this really simplify down to? Just the system and the surroundings. We have to know information about one of those, and you guys can figure out the other one. Does that make sense? Okay. Cool. Right. Internal energy, right? This is just kind of another way of us just expressing the energy within, what do I even say here? Within the system because of nanoscale position of motion. Boy, that sounds fancy. Okay. Right. Blah, 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 blah. Right. Blah, 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 blah. All right. Where is, okay. Next important thing to pay attention to here. So, conservation of energy, right? Is the energy transferred by heat or work, right? So we have the change in energy, delta E is equal to Q plus W, okay? So a couple of important things here. The first important thing to pay attention to is Q. Q is where we're going to spend most of our time studying in this, or calculating in this chapter, okay? So I'm gonna have to give you guys a equation for Q in just a minute, right? But heat plus work gives us the energy of our system, or the change in energy of our system. And there's a couple of initial examples in the textbook, and I believe I have one example for here where we're gonna need this equation, okay? So just find your heat, find your work, add them together, right, to get the energy in the system. This is what's important here, right? Just Q and W and what happens in the system and the surroundings, all this kind of stuff here, right? So if Q is greater than 0, right, heat is transferred in. If Q is less than 0, that means we lose energy, all these kind of things. We're gonna have to, at the end of the day, we're gonna have to pay attention to the magnitude of Q. If Q has a positive value, that's gonna mean something. If Q has a negative value, that's gonna mean something. A positive value of Q means I add energy into that system. That's what I'm trying to tell you guys here, right? If Q is greater than 0, if it has a positive value, I'm adding energy into something, which makes sense. If I give each of you guys 20 bucks, right, and you put that into your bank accounts, now you guys have $22 in your bank account, that's a positive, right? I don't know, wait. Right, you guys with me on this? If I give you something, it's a positive, right? If I ask you guys for 20 bucks for an A on the next exam, right? That's pretty cheap. Right? Oh, sorry, I'm recording this. The professor admits to bribery, right? Wouldn't do it for 20 bucks, right? All right, right? But if I take $20 away from you guys, right, that's a negative thing, right? Negative value. That's all we're talking about here. So just like when we were dealing with charges, and make sure that you guys are specifying +1 or -1, right? Because +1 is very different from -1, right? They have different charges, different ideas, different values, all this kind of thing. The same thing is at work here. Pay attention to whether you have a positive or a negative value of Q, or a positive or a negative value of work, also of W, right? Because that's going to tell us whether things are flowing into or out of whatever we're looking at, okay? So that's what I'm trying to get you guys to look at here, okay? All right, next important topic, heat capacity. All right, so the definition is kind of important here. It's going to tell us the units of things, okay? So the heat capacity is the energy required to raise the temperature of an object by 1 degree Celsius, okay? So a bunch of scientists got together and they started to measure these things, right? And they came up with a definition, right? It's the energy required to raise the temperature by 1 degree Celsius, right? And so you can measure that, you can back it out, and that's going to tell us a little bit about the properties of that material, right? Now we can actually use this because it is an intrinsic value. If we have a bar of iron, right? If we have a bar of iron, then iron has a certain heat capacity with it, a certain specific heat capacity, I should say. And so we can use that to identify unknown metals and things like that, right? Because it's on a per gram basis or a per mole basis, okay? Specific heat capacity versus molar heat capacity. Pay attention to the units with this is what it is, right? If you notice, one of them is in grams and the other is in moles. Can you guys convert grams to moles?
Yes.
Sure, right? It's no different here, right? Any gram to mole conversion, you guys should be comfortable with doing that at this point, right? I believe I kind of drive that point home here on the next slide. I'll give you guys just a second. I'll finish copying this down now. So if we take that wordy definition that we had in the previous slide and just translate it into a mathematical expression, right? So heat capacity or molar heat capacity, right? The heat required equals the mass. Okay, we'll talk about that in just a second. But here, see the specific heat, joules per kilogram degree Kelvin, okay? So when we're dealing with the specific heat capacity, we have units of mass, but we can also see the molar heat capacity, and all that changes is the units of moles down there, okay? Now, one important point here. Are these units always going to be in kilogram? No, they could also be in grams, okay? So just pay attention to the units that are there. These are units of Kelvin, okay? And that's typically what we end up seeing when you guys do a Google search for these things. That's why I'm putting it here. Okay? Let me ask you guys a question. So the previous definition said that we are dealing with this, what is the energy needed to heat 1 gram of a substance by 1 degree Celsius. If I change something by 1 degree Celsius, how many Kelvin do I change that by? Oh, well, 1 degree Celsius, right, is just 1 degree Kelvin, right? So we can usually just interchange those two there, okay? So don't worry too much about that. I'm just giving you guys when you guys go to your friend Mr. Google, and you type it in, you'll typically see kilograms per Kelvin there, right? Or per Kelvin kilograms, I should say. All right. Now, right below that, right, you'll see Q equals MC delta T. So the heat required, right, is equal to, or Q, just heat, is equal to mass, lowercase m, times C, your specific heat, times the change in temperature, okay? So to calculate energy Q, you'll need to know the mass, you'll need to know the specific heat, and you'll need to know the change in temperature. Okay, you guys with me on this? So Q equals MC delta T, right here. How many variables are in that equation? 4, right? So how much of those do I have to give you information about to be able to solve it? 3, right? But that's it. There's going to be a kind of our go-to equation to figure things out. Yep.
I have a hard time understanding how you get units of C. Why is J on top? The rest down below.
Because it's the definition that we had previously, right? The energy needed per gram per degree, right?
Got it.
Okay. Good question. You might see the equation written slightly differently. Instead of mass, we have moles, right? And all that's changing is whether we deal with the molar heat capacity or the specific heat there. How does that change your equation practically? It doesn't, right? The energy is just now moles times the molar heat capacity times the change in temperature. Okay? Same thing, Q equals MC delta T, or Q equals NC delta T. Right? Mass or moles. Good. Say no. So there's tables and tables of this stuff in the book, in the back of the book, I believe, in this chapter itself. So when you guys are going through working practice problems, if you guys need to look up your heat capacities or molar heat capacities, things like that, those are values that are given to you guys, unless they ask you guys to calculate it, okay? So I'm not expecting you guys to memorize any of these things, right? One important thing to pay attention to, here's our buddy water as a liquid, and we see this 4.184, right? So if you guys remember, I just told you guys you would see that, when we're dealing with calories and joule conversions there, right? So there's that 4.184. Pay attention though, right here. Here's water as a liquid, here's water as a solid. We have a different heat capacity. So it's extremely important to pay attention to the state of the matter, okay? Whether it's a solid, a liquid, or a gas. All right? We start to have some problems coming up here now. Yeah. All right. So now that we know everything about everything that we need to know about everything, let's take a look at a practice from here and start to put some of this blah, blah, blah into an example. So, what's this asking? How much energy will be used to heat 500 grams of iron from 22 degrees Celsius to 55 degrees Celsius, right? So what information do I have? I have mass, I have a change in temperature, and I have I have a specific heat here, right? So I have M, which is equal to 500 grams. I have heat capacity, which is equal to 0.451 joules per gram degree Celsius in this case. Could be important. And we have a change in temperature, which is equal to T final minus T initial, right? Where I end up minus where I began, right? T final minus T initial. Yep.
Why are there negative ones after like gram?
Those are, they're per gram per degree Celsius, right? This just to make it easier for me to write this out when I typed it in. Otherwise I'd have to use the terrible equation editor that comes with this stuff. Okay, cool, let's fill in those numbers. So that's equal to 55 minus 22, which is equal to 33 degrees Celsius. So I have information about mass, specific heat, and change in temperature, right? And we know that Q is equal to M, C, and delta T, right? So if we're doing our due diligence here, follow our units, grams, oops, I meant to do that in green. Grams cancel out with grams, degrees Celsius cancel out with the degrees Celsius. So the final units we are left with are units of joules. Why is that important? Well, what are we trying to figure out? In red, we're trying to figure out what? Energy, right? And what unit do we have to report energy in? Joules, right? So make sure our units all settle out. And what I got for this is, what is it, 7442? Okay. So let's think here for just a second. Okay. I know the question doesn't quite ask this, but just for argument's sake. So what does this value mean? So this means that I have to put 7,442 joules into that iron bar, right? There's an iron, yeah, iron, right? Into that iron bar. So the Q for the iron would be what? Positive 7,442. You guys with me on this? Where did that energy come from? The iron bar is the system, so the energy had to come from the surroundings. So what about the energy of the surroundings? The surroundings had to what? Lose 7,442 joules of energy. Why? Gotta maintain the balance, right? The yin and the yang, the light and the dark, the plus and the minus. Okay, what you put in, you have to get out. Because as the saying goes, garbage in, garbage out, right? You guys with me on this? So be careful about what the question is asking also. If it's saying how much energy was put into the iron bar versus how much energy was lost from the surroundings, then we have to really pay attention to whether it's a plus or a minus, okay? idea, a little bit trickier here. What formula are you guys gonna have to use? Q equals MC delta T, okay? So find your useful information, pull out those numbers and start to set up your equations. Careful of your units though, right? Careful of your units. Yep. What's T stand for? Not energy, but temperature, right? So energy is Q, right? Well, that's value of Q, right? Temperature is gonna be given in units of Celsius, or Kelvin. Mm-hmm. You would be careful, right? It's not 24.1, it's 24.1 kilojoules. So be careful of your units with that one. Yeah. And you got your negative from there. Good. Just be careful that not 1.5 or initial temperature. So you can plug that in. Otherwise, can't solve that, right? Okay, wait. Luke is correct, yep. Otherwise, if you leave that as positive, then it's gonna throw off your number at the end. Cool. So now we gotta get it all set up, right? You've got mass, you've got C, you've got delta T, and you've got Q, right? So now we just gotta rearrange for whatever's missing. That's what I would do, yeah. Well, what I would do is, multiply those, and you could multiply that, times that. There's a couple different ways of solving it, but it's, like, I'm not joking with you guys when I say, right, I just find the simplest way to do it. Yeah. No, right, because, so, this is. Yeah. So, but real quick before
you got an answer, right, which is good, but then you're looking to say, does my answer make sense? So you're telling me the final temperature is higher than the initial temperature. But what does the question ask? It's saying it's lost. So something got messed up along the way, right? So it said the energy is lost. Yeah, no, the math is identical, it's just don't forget that negative sign, because otherwise it's gonna give you an answer that it doesn't make sense, right? How can you read energy increase? Right, so don't forget that negative, because that makes a big difference. So now, does your new answer make sense? You lost energy and the final temperature is lower than what it started. Right? Does that make sense? Yep.
Cool, alright, good. That's really awesome. I've been going around and you guys have been getting a lot of right answers. Which always means what? Harder exam questions, right? So you got, remember, you guys gotta play the game here, right? You gotta throw the questions in class. I'm like, oh my gosh, these guys don't know anything. Then the questions end up being, you lose 1 joule of energy. How much energy is lost? 1. Everyone gets 100, it's good, all right. So real quick, let's get this knocked out then, but you guys, I saw a lot of correct answers here. So, I'm telling you guys 24.1 kilojoules of energy. So whenever you see energy, what does that mean for us in terms of alphabet? That is our Q, right? 24.1 kilojoules, okay, is lost by a 251 gram block of aluminum. Good, so there's our mass. We have information about specific heat, 0.902 joules per gram degree Celsius. We take a quick pause here. This is in units of joules, this is in units of kilojoules. So what do we have to pay attention? Convert one to the other, right? So I'll do the math, it's a little bit simpler for me. Right, so this is 24,100 joules, right? Cool. Good? And then we have our buddy delta T, right? Which is equal to T final minus T initial. And we have initial temperature of 125, so we have T final minus 125 degrees Celsius. All right, let's put it all together. So 24,100 joules equals mass times specific heat, 0.902 joules per gram degree Celsius. I just ran out of room, so let me do this real quick. Times T final minus 125 degrees Celsius, okay? But one thing that I'm missing, and it's the important thing, what does this 24,100 represent? How much energy I lost, right? This is extremely important, how much energy I lost. So negative 24100. Okay, I'll see you guys on Friday. Let's see if you guys can finish up the math.